sample complexity of partition identification using multi-arm bandits. So I'll explain to you, I already mentioned to you this pure exploration problem where we want to find the best arm with the best mean. And now we'll kind of put that in a more general framework, more abstract framework, and see how to address that problem. So this is what I discussed with you earlier. This is a classical problem in Monte Carlo simulation community. Finding a distribution arm with the largest mean. K arms, you want to find the arm with the mean which has the largest value. I mentioned this picture to you earlier. So now we'll just generalize that because this came up to us, we were dealing with some finance problems, and we naturally saw some problems which are kind of a more general version of this. So we want a framework which captured all of this in a unified manner. So suppose now omega is a collection of vectors. Omega is, small omega is nu1 to nu k, so it's k distributions, so k arms, k probability distributions. So each set of k arms now becomes a point in my big universe, big omega. I can express my big omega as a union of p partitions. AI is a disjoint. So I have these different sets. Each set is collection of all these arms. So I'm given some omega which the learner or the algorithm does not know. It needs to figure out which partition is this omega coming from. Is this clear, the abstract problem? As an algorithm, you give me some arm, some collection of arms with some probability distribution. I don't know which they are. I know these partitions A1 through AK. I need to figure out which partition does this vector of arms belongs to. So our best arm problem corresponds to these partitions being, this is a set where the ith arm is with the largest mean, first arm with the largest mean, second arm with the largest mean, third arm with the largest mean. And you give me this vector of arms, I need to figure out which set it belongs to, which arm has the largest mean. So best arm naturally fits into this framework, right?
So it's kind of classification of these set of k arms?
It's kind of a testing of hypothesis.
Okay.
Right, you're testing a hypothesis, composite hypothesis, which one it belongs to. So it is a classical problem in statistics, but kind of problem which was studied by Chernoff, famous Chernoff, if you know that name, and his student Albert, but largely ignored for a long time after that. And now people find that they're rediscovering the techniques which are kind of already there in some form. So let me tell you but what they don't do is they don't study the geometry of these things, which is what we are going to do. So finding if a vector of means lies in a half space. So this is one example. I give you this vector of means, and the question for you is, does it lie on this side of the half space or this side of the half space? So half space is given to you. A1 x1 plus A2 x2 is equal to B. I mean, this is the hyperplane. And does this collection of two arms, does it lie on this side or that side? This is set A, and this is set A complement. So it's like, okay, I have these two projects in my financial world. I have a simulation model which can tell me what the cash flows are going to be from these two projects. Is the profitability from these two projects above a threshold that I'm happy with or no? Then that could be one example of these things. But this is a generic problem, finding whether this vector belongs to this side of a hyperplane or this side of the hyperplane. It can be of importance in many, many settings. Or I can give you a polytope. So it's just an intersection of hyperplanes. I'm given this point. Does it lie in the polytope or does it lie outside the polytope? So that's the kind of questions I'm going to ask you right now. So is this clear now? I've told you earlier that we have these many partitions, but right now I'm just looking at two partitions. Either this vector of arm lies in a polytope set or its complement, A or A complement. So that's a decision you have to make. And basically what you want to do is you want to sample each of these arms and make a decision quickly. It lies in the polytope or outside the polytope. You want to make that decision as quickly as possible, controlling the probability of error to less than or equal to delta. Right? That's the game right now. That's what we want to do. Is this problem clear to everybody? It's kind of what's nice about it, it's easy to state and understand that you're given a k distributions, arms. You can sample from each one of them. You want to know whether this vector belongs to this set or the other set. By sampling, you want to make this judgment as quickly as possible, controlling the probability of making a wrong judgment to delta. Given you're going to do that, you want to make this judgment as quickly as possible. So again, given this arm, does it lie in a convex set or it lies in the complement of a convex set? So one can say a lot about this geometry, and that's where I'm going with this talk. This is something which people have not looked at. Okay, and this was the problem which actually started us to this literature, finding an arm with a mean above a threshold. So omega is a collection of vectors, nu1 to nu k. Nu I is a probability distribution with mean mi. So given such a vector of arms again, and a threshold u, somebody's giving me a threshold u, need to determine if the vector belongs to set A or A complement. A is the set of all omegas, all instances, where mean is above u. And A complement is set of all these vector arms, where all the means are below u. So that's a decision that has to be made. You're given a vector of arms. Is there any arm amongst them with a mean above threshold u? Or are all arms in this with mean below threshold u? That's a decision that has to be made, and as quickly as possible. This comes up very nicely, very naturally in Monte Carlo simulation. Maybe I'll talk about this in Monte Carlo simulation, nested simulation applied to finance. So I'll talk about this maybe towards the end of this talk. This is the picture. So I'm given these arms. Some of them have arms have mean above u. Others have means below u, and you need to find out whether there's an arm with mean above u or not. What's going to be elegant about this? So the punchline here is as follows. That if you're going to sample from these arms to make this determination, if indeed there was one arm above level u, then optimal strategy should be to quickly find such an arm and spend all your computational effort there. Ignore everything completely. There could be 5 arms above this. Just ignore the other 4. Focus on the best one. On the other hand, if all the arms are below u, then you have to painstakingly sample each and every arm and rule out the fact that it could be above you. Then you have to spend a lot of computational effort. So this is a game of how to optimally give your simulation resources or sampling resources. And problem becomes much harder if all the arms are below you, much easier if some arms are above you. So it's a kind of has a nice intuitive feel that we understand the hardness of these problems. So the agenda for this talk is we'll develop a methodology for computing lower bounds on computational effort for delta pack algorithms. So this is going to be something very new and perhaps technically demanding if you're not familiar with this kind of literature. How do you come up with lower bound on algorithms? So delta pack algorithm I've described to you. Right? They're going to sample adaptively, tell you which arm is better or which partition does this vector of arm belongs to, controlling the probability of error to delta. That's their property. So amongst all the delta pack algorithms, I'm going to say every such delta pack algorithm has to satisfy some lower bounds. Has to spend so much time at least on each and every arm, no matter what algorithm you come up with. So we need a theory to come up with these lower bounds. So that I'll tell you about. That's an elegant theory. But you come up with precise lower bounds that every delta pack algorithm has to satisfy these lower bounds. That gives me a nice optimization problem which depends on the geometry of the underlying problem. I'll solve that geometry, and that will actually give me a delta pack algorithm, how to do things, so that I actually match the lower bound. Your question earlier, can we come up with algorithms which actually match these lower bounds? And you actually can to a large degree. So we'll just talk about that here. So great deal of elegance is built into these things. So this involves exploring the geometry of the problem structure and use of duality theory. So how many of you are familiar with duality in linear programming? Of course, yeah. But some of you, so not too many. But it's very nice that it comes, these kind of dualities, convex dualities come very naturally in this setup. So you have to exploit them to get these answers. So we developed delta pack algorithms with matching computational bounds in general settings, including the threshold problem which I showed you. Does the arm above a threshold mean exists or not? The half space problem, the convex and the complement of the convex set problem. So in all of these, one can say what the lower bounds are going to be, and then actually develop an algorithm using those lower bound structure, which is with matching the lower bounds. Nested simulation crucial for financial portfolio risk. We discuss illustrative problems. So I'll just discuss one problem here, where all of this fits in. I may have the time, so I'll do that. So some literature. So I've not done any literature review so far, so let me do it right now. So this pure exploration problem, there's a lot of literature, by the name of ranking and selection. You're given these arms or distributions, you want to rank them in terms of their mean or find the arm with the largest mean. So So that's well studied in statistics. Bekofer has a famous paper in 1968 that talks about uniform sampling, sample each arm uniformly. Paulson talks about elimination-based algorithms. Sample all these arms and throw away arms which don't look like they're going to make it, that their means are big enough. But all of this is kind of, a lot of the key ideas are already there in Chernov's paper in 1959 and his student Albert's paper in 1961. So a lot of good ideas are there in these papers. They should be more well known. But these are somewhat technically demanding papers to read. Simulation theory has been worried about this, so these are some of the names here. I worked on this some time ago. Computer science works a lot on this pure exploration problems. So this is computer science and learning theory literature. It's quite elegant, all of this. So Garavier, Kaufman, Kappe-Garavier, and Garavier and Kaufman, we borrow a lot from their techniques. The way it actually worked was that we devised some techniques, and then we discovered that, okay, 2 years ago they had done this already. And then we learn a little bit from what they did and kind of incorporate them in what we do. This is how research works, right? And regret minimization, which I mentioned to you. A key seminal paper is Lyon Robbins, 1985, but then there are a lot of other papers in this. So very active area of research. I mean, I'm not mentioning it, but thousands of papers get published every year in this area. Okay, so what's a delta pack algorithm? So remember where we are going with this is, we are solving this partition problem. We are given a vector of arms. We want to figure out which partition it belongs to. And we are going to look at delta pack algorithms. And these are algorithms with the following structure. An algorithm specifies an adaptive sampling strategy. It adaptively tells you in this vector of arms which arm to sample from next. It looks at the data so far and decides which arm to sample from next, right? 3 arms are given to you. It decides first arm sample. Okay, the value looks like this, so let's sample the second one, so on and so forth. Then it comes up with a stopping time. This is the time to stop. So there's a rule. Now I stop. And finally, it gives a recommendation. This set of arms came from this particular partition. Okay? So that's the problem we are focusing on right now. So and this is a delta pack algorithm. So algorithm is said to be delta pack. So this is any algorithm. And it's said to be delta pack for a given partition of omega. If for any mu, this is just a vector of distributions in omega, it announces in finite time, tau, that mu belongs to a partition aj with probability of error bounded from above by delta. Right, so these are properties we are going to demand from the algorithm. Is this clear what delta pack algorithm is? So for these algorithms, you're going to derive lower bounds. Because it has this property that you give it any omega, any instance of arms from this whole space, big omega, that imposes some constraints on, it forces the algorithm to sample so much on each arm. So we'll talk about that right now. So this relies on change of measure arguments that go back to at least Lyon Robbins, but actually go back even to Chernoff and people before that. In testing of hypothesis, these arguments have been around for a while. So my guess is many of you will find these arguments a little complicated if you've not seen these terms before. Have you seen change of measure arguments in probability? Likelihood ratios? Oh, you've seen them. Okay, good. So let's consider a simple setting. And this is a nice bound that Kaufman, Kappe, and Garavier came up with. It's a non-asymptotic bound. That's a nice part of it. It's true for any delta. So if mu is my arm, mu and mu2 are 2 distributions, and it belongs to set AI. And nu is another set of distributions which belong to AI complement. So the algorithm, it's observing data that's coming. Suppose the data is coming from here. When this guy is sample, I observe sample from this distribution. When this arm is sample, I observe a sample from this distribution. It has to decide whether this data is coming from partition AI, and it's worried that maybe it's coming from partition AI complement. Maybe it's actually generated from nu. So it will tell you that it came from AI only when it's convinced that it did not come from AI complement, right? Only when it's convinced that this data did not come from this, for example, this candidate nu in AI complement, right? It has to be convinced that if indeed it had come from nu, probability of seeing this data is very small. It's less than delta. It wants to be convinced of that. So that imposes the following constraint. It must be that on this arm, the number of samples I generate, n1 is the number of times arm 1 is pulled here, under distribution mu, if the data was coming from mu. This expectation times Kullback-Leibler distance between mu1 and nu1. So Kullback-Leibler distance is defined as follows. Log of d mu a upon d nu a x. This is just the Redon-Nikodym derivative between two measures. This is the likelihood ratio between two measures, weighed by the probability in the mu of a. So I'll explain to you why this is the natural measure, but clearly this theorem is telling you, this result is telling you it is the natural measure. Kullback-Leibler distance between mu1 and nu1, plus the number of times, expected number of times the second arm should be pulled, weighed by the Kullback-Leibler distance between mu2 and nu2. This summation together must be greater than log of 1 upon 2.4 delta. So this inequality is a non-asymptotic inequality, which was given by Kaufman, Kappe, and Garavier. Everyone kind of knew this result asymptotically as delta goes to 0, but the fact that this is true for any delta was shown by these guys, and it's quite elegant. What's going on here? What it's saying is that if mu1 and nu1 are very close, if distribution mu1 and distribution nu1 are very close, and what do I mean by close? That's measured by this Kullback-Leibler distance. It's kind of a notion of distance. You know, mu1, nu1 look very similar, then this number is going to be small. If mu1, nu1 look very different, this number is going to be huge. So if they're very close, then I need a lot of samples to separate them. If these two are very close, I need a lot of samples to separate them. But the sum must be greater than or equal to this if I have a delta pack algorithm. So it's it's extremely elegant way of getting this lower bound on the effort required on each arm if it has to be separated from distribution nu, which belongs to another partition. So now I'm going to spend a little bit time digging deeper into this. So n1 plus n2, by the way, is just tau. That's the total number of samples I've generated. n1 times arm1 was pulled, n2 times arm2 was pulled. Kullback-Leibler distance is what it is. Okay, so let's see, rationale for this lower bound. So suppose, see the algorithm, it's a delta pack algorithm. It's only going to see data. It will sample from all these arms and it will only see data. It doesn't know anything else about the distributions. So it's going to just observe x1, j less than or equal to n1. So these many samples from arm1, these many samples from arm2. Right? That's the data it saw. And suppose the algorithm is delta pack and it announced that this belongs to set AI. Now let's see. Suppose the underlying distribution from which these samples were coming, mu, belong to AI, and nu is another distribution which belongs to some set in AI complement. Then the algorithm looking at data x and announcing AI as the partition that this data is coming from, that should have probability less than or equal to delta if the true measure was nu, right? If indeed the underlying measure was nu, then the algorithm is, by definition, it should ensure that this decision should have probability less than or equal to delta. On the other hand, if the underlying data was coming from mu, and the algorithm says x belongs to AI, that should have very high probability, right? So this is the properties of the algorithm. It has these properties that if it looks at data and makes judgment, it should satisfy these inequalities. The best part, the beauty of kind of getting a lower bound on this setting is that these two probabilities can be related to each other through change of measure argument, through likelihood ratio. So again, this kind of goes back a very long time. This is well-known stuff in probability. Yeah?
Nu belongs to A complement.
Nu belongs to AI complement.
Then the equation should be A complement. X follows A complement. First equation.
Oh no. So it's so this is no. So in that case, saying that x belongs to AI is making a wrong decision. So hence this probability that should be less than or equal to delta. And x belonging to the right partition should have probability 1 minus delta, but this probability should be less than or equal to delta because it's the wrong thing. While in this case it's the right thing, so probability should be greater than 1 minus delta. That's exactly what we're going to exploit.
This is like controlling the probability of type 1
Yeah. That's right. And you can link the two through change of measure argument. So this is again going to give us the inequality that we are interested in showing. Just linking these two gives us these inequalities. But let me tell you a little bit more about this, since we have time. So how do we link these two probabilities? Well, let's focus on this again. P nu x announces AI. I'll express this now under a measure E mu, expectation under measure mu. And the way I do it is I just write the likelihood ratio here, right? That's how I go from one expectation to another expectation. This likelihood ratio is now just d nu A is the ratio of the two densities under measure nu A and measure mu A for all the samples j from 1 to NA, and for all A taking values in this case 1 and 2. This is my likelihood ratio of, and this is the indicator that X was seen and was announced to belong to AI. This likelihood ratio is just a product of individual density. You know, it's like saying that whenever I generated this XAJ sample, under mu its density is given by this form here, under nu it's given by this form, so I correct by having this likelihood ratio here. But the point is this is a product of many terms. The product, if I exponentiate it, just becomes a sum. This is just a log here. J equal to 1 to NA minus A equal to 1 to 2, right? Now what do I know? So I'll just give you a heuristic argument, but it's kind of persuasive. This should be less than or equal to delta, right? This term here, suppose I didn't have this indicator. I can apply Jensen's inequality. How many of you are familiar with Jensen's? So Jensen's inequality is very nice inequality which allows you to kind of get bounds on expectations of convex functions. Since exponential is a convex function, I get a lower bound if I put this E mu here inside the exponential function. So ignore this indicator function for now. If I bring this expectation here, this is exactly this by Wald's identity. So what is this? So what is Kullback-Leibler between mu and nu A? It's exactly the expectation of log of this density function, likelihood ratio, with respect to measure mu A. Right, that's how we define Kullback-Leibler. Let's just go back. Sorry. It's log of d mu A by d nu A with respect to measure mu A. So when I take an expectation of this, I get expected value of d mu A, d nu A with respect to measure mu A. That's just Kullback-Leibler distance. And plus I get an expectation of number of terms Na. That's A mu of N of A. So I get this. This has to be less than or equal to delta. That means this term here has to be greater than or equal to log 1 by delta, which is the inequality which I showed you here. Now you say, okay, why is this 2.4 here? But I also got the indicator for you. So there's a lot of elegance which goes into this. You know, the fact is, these things were asymptotically known for a long time, but this result, this was asymptotically known for a long time, but for a fixed delta, this was known only recently, just a couple of years ago. So the convexity arguments, you partition the space, you use different change of measure. It's a little elegant argument that makes this work, which allows you to get rid of this indicator function. But in any case, now I think we understand this well enough that you can take these inequalities as a given. Right? Any delta pack algorithm, when it has to spend this much effort on arm 1, when the underlying measure is mu, this much effort on arm 2, because it has to compare with any measure nu1 and nu2 which belongs to the other partition. So this inequality must be true. This is what we are going to use now going forward. So, but before I do this, let me just confound the complication a little bit more. So I'll tell you some more thing which is interesting. We are going to need some restrictions on the underlying distribution of arms. So whatever I derived for you right now, you know, I told you that I have this big space, universe omega with partitions and these vector of distributions. I didn't make any assumption on the distributions. This was true for any distribution whatsoever. So, but going forward, when you look for algorithms, we are going to need to make this assumption on distributions. So why do we make those? Why do we need to make those assumptions? I'll just give some motivation for this. That some restrictions are going to be necessary on distribution of underlying arms, because otherwise you don't draw any conclusions at all. The problem becomes too hard. Big picture I'm saying is that you can come up with two distributions which belong to different partition and which the Kullback-Leibler is arbitrarily close. So you really can't separate them. The amount of effort required is going to be infinite. So this is my work with Glenn, some restrictions on underlying distribution for fast algorithms. So consider now an instance where mu is two arms, mu1 and mu2, with means m1 and m2, m1 greater than m2. So one arm has distribution mu1 with mean m1. Another arm has distribution mu2 with mean m2. So your delta pack algorithm will look at samples from these two and conclude that this is the best arm controlling the probability of error to less than or equal to delta. This is clear to you, this picture, the green color, you can see? Okay. Now consider another instance. This is again two arms. First arm is again mu1 as before, but the second arm is nu2. Nu2 has mean M3. Sorry. And M3 is bigger than M2, M1. M3 is bigger than M1. So if your algorithm was to look at this instance, it will generate samples from these two arms. And now if it were to conclude that this arm has the largest mean, that would be a wrong conclusion. Probability of that should be less than or equal to delta. So this is an arm which belongs to the other set. It's other partition. Right? So the inequality which I showed you should hold between these two measures, mu and nu. But since mu1 is same in both of them, Kullback-Leibler distance between them is going to be 0. So really what this is going to give me is inequality of the following form, that the number of times arm 2 should be pulled under measure mu times Kullback-Leibler distance between mu2 and nu2 must be greater than or equal to log of 2.4 delta. If you agree with my earlier result from the Kaufman paper, this inequality follows. Right? So the algorithm, delta pack algorithm, has to spend some time on this arm because it's worried that the data it's seeing from here could actually be coming from here as well. So it has to spend enough time here to become comfortable that this data is not coming from this arm here. Basically, it has to vary between these two arms. And that gives a constraint that E mu of n of 2 times Kullback-Leibler between mu2 and n2 should be large enough to control the error if the two data was coming from nu and it concluded that it's actually coming from the measure mu. So this tells you that E mu of n of 2, expected number of times arm 2 is sampled, must be greater than or equal to, I'll just take this in the denominator, and I'll now look at all nu of 2 with the property that M3 is bigger than M1. This was a defining property, right? It had tried to separate from this. So I'll look at infimum, smallest of these values, and that gives me an inequality on E mu of n2. And now the simple observation is that I can always come up with a distribution nu2 which is arbitrarily close to mu2 in Kullback-Leibler distance and arbitrarily far in terms of mean. And what that means is that this will be infinite basically. This infimum will be 0 because it's arbitrarily close, so I can make it as close as I want. So this is going to be infinite term here. That means the lower bound on expectation is infinite. So if I allow all such distributions to exist, if I say my delta pack algorithm works on all of these distributions, then we have a problem. Then it's going to need to spend infinite amount of time on the second arm to separate these two. Let me just say pictorially what I'm saying. Let me come back to this comment a little bit later. That your underlying distribution mu2 could have been this red distribution here. No, this green distribution here. But think of another distribution which is the red distribution which takes a little bit of mass from here and throws it in the tail. This point is well chosen, right? So these two distributions can be shown to be arbitrarily close in Kullback-Leibler, as close as you want them to be. But by choosing this point carefully, their expectations can be arbitrarily far. So your delta pack algorithm, if it works on both of these distributions, then it has to separate these two distributions, all of these things. And that's going to take a lot of work. So that's why we assume distributions are bounded. Then you don't have to worry about these tails causing problems. Right? So that's what's coming up back here, that this is going to be infinite. So Glynn and Juneja show that if distributions are unbounded, this can be made arbitrarily small, hence finite expected time algorithms, not feasible without further restrictions. So you need to have further restrictions. Kind of an obvious point, but just drilling it home, that there have to be these things. And then with explicit upper bounds on moments of arm distributions. So what kind of restrictions do you need? You could say that in my universe of distributions that my delta pack algorithm is looking, everything is bounded. That's one restriction. But maybe weakening that could be that everyone has third moment or second moment which is bounded by some known constant. No moment is more than 25. I know that. In that world, one can devise algorithms. In fact, one can divide algorithms which match the lower bound, but that's my ongoing work right now with a student. That's hopefully something we'll have very soon. All right, so that was so big picture so far was, if you ignore the mathematics, that when you have a delta pack algorithm working on the universe, you can't assume that all the distributions are arbitrary. Because then you'll have real trouble separating distributions which are very close to each other. Now, I'll make life really simple by assuming that distribution functions that we are going to consider come from one parameter exponential families. This is commonly done in statistics. It simplifies things a great deal. So what that means is I'll only look at distributions which look like this. Now, don't get hung up on this form. At the end, what I want from this slide is something very simple. So I'll just tell you what that is. But let me just explain this form nonetheless. This is, x times some parameter theta. This is some reference measure rho of x. So this is some measure that I have. It doesn't even have to be a probability measure. It could be discrete. It could be continuous. And then I have one parameter here. And this lambda theta is just something which makes this a probability distribution. This is a normalization function. So this structure can be shown to be true for binomial distribution, Bernoulli distribution, Poisson distribution, Gaussian with known variance, gamma distribution with known shape parameter. So there are a fair amount of distributions which fit into this framework. So I'll restrict myself to just to these distributions. But what I want to take from this is that each distribution here, because it belongs to this family, can be identified by a single parameter theta. There's one-to-one mapping. So when I say a distribution, I can also might as well just say the mean. So only one distribution will have a particular mean. There's a one-to-one mapping. So henceforth, I'll only talk about means. I won't talk about distributions. Yeah?
Can we weaken the assumptions on these distributions with some other measure of divergence between things? Like here we are using KL divergence. Right?
So KL came up in the lower bound. So you couldn't have avoided that. You can't say that Basher sign distance works or something. Lower bound depends upon KL. KL is the right measure for separation of two distributions in this case. Every algorithm has to have this lower bound where KL shows up. It's not something we chose. Right. But now the point I'm making is simply going forward, I'm restricting my discussion only to those distributions which are from the single parameter exponential family. So when I talk about a distribution, I may as well talk about the mean because they're one-to-one related to each other. So what that means is in the remaining talk, my big omega is a collection of vector of parameters in Rk. So each distribution, each vector of distribution is just a point in Rk, and I have a collection of these parameters. So now I can talk about the geometry. It makes me see the geometry much, much more clearly. This is what people have been doing, by the way. It's not. This is what the computer scientists in the last learning theorists have been doing in the last 5-6 years. So now what happens is that my key inequality for delta pack algorithms, recall it's just specified k arms, it would just be amount of effort I spend on arm A equal to 1 to k in expectation, times Kullback-Leibler distance between mu A and mu A. Now these are means, right? This should be getting equal to log of 1 upon 2.4 delta. Where recall that, again, this summation here is just expected value of tau. So the point is this, that this is kind of where things become kind of fun. Every delta pack algorithm now has to satisfy this thing. Every delta pack algorithm in this nice space of single parameter exponential family has to satisfy this inequality. And the computational effort of that algorithm I'm going to say is E of tau. It's just this summation. This is the amount of samples I'm generating on average, right? So let me just let me just make this, parameterize this, and in the space of all parameters here, let me find the ones which have the smallest this thing. And that's my lower bound to the overall problem. Right, so what I'm saying here is, I'll just call this as a variable t of A for each A, because every delta pack algorithm has to satisfy this inequality. Log 1 upon 2.4 delta I've just replaced by 1. I just normalize everything by that. I'll bring that up later. No need to worry about that. So TA into Kullback-Leibler between mu and nu A. This should be greater than or equal to 1. And this should be true for every nu in my alternative hypothesis AI complement. Right? I have to compare with each and every one of them. So each one of them, this should be greater than or equal to 1. So infimum over this should also be greater than or equal to 1. I look for TAs which have to be non-negative. And I look for TAs which are minimum, which satisfy these constraints, which every delta pack algorithm will satisfy it. And amongst all such variables, let me find the ones which have minimum value of this. This gives me a lower bound on my computational effort. Right? That's how I'm getting the lower bound. And what's nice about this is, if you think of this, suppose your news were actually taking finitely many values. Then these are just finitely many constraints. So it's a nice linear program. If you allow your news to take uncountably many values, then it's a semi-infinite linear program. It's a linear program with infinitely many constraints, but still a linear program. What's nice about a linear program is that you have an elegant duality theory, and that gives you a lot of insights. That's how we approach this problem. We wrote a linear program, we wrote the dual, we guessed what the solution is going to be, and we were able to solve all kinds of things. And then we realized that there's a simpler way to do these things. And the simpler way is using the min-max theorem. I'll tell you what that is. But it's a famous theorem. It kind of crystallizes the duality. I'll talk about that as we go along. It's a well-known theorem. It goes back to game theory, the time of John von Neumann. He used the simplex min-max theorem. That kind of made game theory possible. And thereafter, economists extended it in a variety of ways. It comes up naturally in this setting. Comes up as follows. So this is my optimization problem now, right? From the lower bound theory, I got this nice optimization problem. That if I solve this, I get a lower bound on my computation. Now I can just take this summation TA and divide both sides by it here. Then this becomes W of A, when now W of A is it lies in simplex. Summation W of A is equal to 1, WAs are non-negative. So that's a nice structure. So W of A lies in a simplex. And here I have 1 upon summation of T of A. So minimizing this is same as maximizing 1 upon summation T of A. Yeah, so we are 3 minutes, right? Right. So basically this optimization problem can also be written as, you look at infimum nu in AI complement, this summation. See, whatever this summation I get, I want to choose my weights so as to maximize this. So it's a max-min problem now. It's like I choose the weights W of A. W of A, think of as probabilities. At any step, I'm going to choose with what probability arm A should be chosen for sampling. And the nature then chooses the worst nu that I have to contend with, which minimizes this guy here. This is something which I want to maximize. By the way, this max-min formulation, although not in this lower bound delta pack setup, was already known to Chernoff when AIs were finite. He kind of intuitively came that this should be the way to come with an algorithm. That nature finds the worst point that you have to compete with. His way of approaching this was through the generalized likelihood ratio method. I don't know how many of you are familiar with this. In testing of hypothesis, when you have a composite hypothesis, then you have a generalized likelihood ratio method. And using those arguments, he came up with this max-min formulation. The nature tells you that this is the design you have to worry about the most. This is the alternative hypothesis that you have to worry about the most. And your flexibility is that you can choose these randomized weights. So yeah, so a lot of these ideas were kind of there. Of course, we are approaching it, beyond this, he just assumed that you can solve this problem. And what we are going to do is actually solve this problem in a variety of geometries. And there's lots that can be said. And it's important to solve this problem because this is going to be key to your algorithm. You'll have to solve this many, many times. All right, let me stop here. I think now it kind of becomes more fun. The geometry comes into play. So I'll show you pictures after this. But let's come back to that in half an hour.